Moment distribution. This demonstration will show how an applied moment at the center span of a two-span continuous beam is shared by the two spans according to their stiffnesses. We will first examine the theory behind moment distribution and then continue on to a physical example complete with strain, deflection, and rotation measurements, which will allow us to compare expected and actual results. The data exploration and analysis program we are using is National Instruments LabVIEW, which in conjunction with various testing instruments, which will be explained shortly, will allow us to seamlessly compare our actual results with what was expected. Without further ado, let's get into the theory. The stiffness of a beam is given as 4EI over L. In this particular case, EI equals 1.9 times 10 to the 6th Newton millimeters squared. Therefore, for span AB, K1 equals 12,667 Newton millimeters, and for span BC, K2 equals 19,000 Newton millimeters. The next step is to determine the distribution factors at each support. These factors are determined by dividing the stiffness for the beam of interest by the sum of stiffnesses at that location. For example, distribution factor BA is given by dividing the stiffness of span AB by the stiffness of span AB plus the stiffness of span BC. These factors will tell you how much of an applied moment will be carried by each span. Here is a summary of the distribution factors. The next step is to realize that a moment applied at the pinned end of a pinned fixed beam will carry exactly half that moment to the fixed support. For example, once a moment has been distributed to span AB from the node B, half that moment must be carried to support A as shown here. For this demonstration, we will show how a 2,000 Newton millimeter applied moment at the center span will distribute to the supports. This moment is applied by placing 20 newtons of load on a 100 millimeter lever arm at the center support. The theoretical moment distribution is shown in this graphic. According to the distribution factors, 40% of the 2,000 Newton millimeter moment will be distributed to span AB and 60% to span BC, 800 Newton millimeters and 1200 Newton millimeters respectively. Of those loads, half will be distributed to each span's fixed end, 400 Newton millimeters to A and 600 Newton millimeters to C. These are the reaction moments. Now we will take a look at our experimental setup. Inclinometers have been installed at each support to give values for the slope of the beam at those locations. 5 strain gauges have been installed on each span, which allow us to find the curvatures at those locations. Subsequently, the bending moment, shear, slope, and deflection diagrams will be calculated from this information. The relationships we are interested in are displayed here. Curvature, moment, shear, slope, and deflection can all be calculated once we have the strain measurements. These functions have been built into our LabVIEW program using strain as the input. 2 LVDTs, or linear variable differential transformers, have been installed on each span. These devices measure vertical deflection and will be plotted at their corresponding locations on our calculated deflection diagram. Now that we have somewhat of a grasp on the engineering calculations behind the curtain, we can get into the LabVIEW program functionality and experimental results. This interface is where we tell the program what loads are applied and where they are applied. Point loads and locations are entered at the top, and applied moments are input in the center. We can also tell the program whether or not a support is locked at any step of the demonstration. It also contains valuable information regarding rotations at the supports and deflections at the 4 predetermined locations along the beam. Towards the bottom of the interface, you can see 3 dials and 4 meters, indicating the rotation at each support as well as the deflection of each of the LVDTs in real time. Here is the initial setup of our beam. Supports A and C are locked, and support B is free to rotate. No load has yet been applied. These are the corresponding empty graphs for shear, moment, slope, and displacement. Now let's apply a moment at the center support. Stephen is now applying a 2,000 Newton millimeter load at the center support in 500 Newton millimeter increments. You can see the dial at the center support rotate while the outside supports remain motionless. He is now locking the center support to prevent rotation for the next step. As you can see, we finally have some data. The expected results are shown in red and the experimental results are shown in green. You may also notice that the experimental moment diagram most closely matches the predicted result. This is because the moment is proportional to what we are measuring, the strain. We only have 10 strain gauges for a 1000 millimeter beam, and as we perform more and more calculations, our results will differ from what is theoretically expected. At the end of the previous step, Stephen locked the center support, so the next step in determining how our applied moment distributed is to unlock the left support, releasing the moment there. As you can see, the center support is now locked in our LabVIEW interface. This is indicated by the neon green light at that location. The left support is now unlocked, and you can see a rotation on the corresponding dial. Here is what is physically taking place during this step. Watch the left support dial as DK releases the rotation. The moment at the left support is now 0, while the portion of the moment diagram over the right span is unchanged because of the locked rotation at the center support and subsequent isolation of span BC. Now we will load the left support with the theoretically calculated reaction moment at that support, bringing the rotation back to 0. This simulates the reaction moment and will verify that our calculation using the moment distribution method is accurate. A moment of 400 Newton millimeters is applied at the left support in our LabVIEW interface while leaving the support unlocked, and the corresponding slope is now 0. Now let's watch this in action. Now that we have simulated the support reaction in the initial condition, the shear, moment, slope, and deflection diagrams are identical to those of the initial condition. So far, the moment distribution method has proven correct. Now we will lock the left support at its current rotation and unlock the center support. There will be virtually no change in the behavior of the beam, once again because of the simulated support condition at A. Here you can see the LabVIEW interface corresponding to this step. The left support is now locked and the center support is now unlocked. DK is now locking the left support and Stephen will unlock the center support. Notice there is virtually no change in the beam. The shear, moment, slope, and deflection diagrams are identical to the previous step. Now we will lock the center support, unlock the right support, and repeat the procedure we performed on the left span of the beam, once again on the right. The center support has been locked and the right support has been unlocked in the LabVIEW interface. Notice how support C is experiencing some rotation at this point. You will be able to see the beam adjust as the right support is unlocked. The diagrams over the left span of the beam remain unchanged. However, the moment at C of the right span is now 0 due to the release and rotation. Now we will apply a moment at the right support, simulating the support condition, exactly how we did for the left span in the previous step. A 600 Newton millimeter moment will now be applied to the unlocked support C, simulating the fixed end boundary condition. The slope will now be brought back to 0 rotation at support C. Behind DK, you can see the rotation of the right support returning to 0 as the 600 Newton millimeter load is applied. The diagrams are once again identical to those in the initial condition. Now let's see what happens when we unlock all the supports. If our prediction is correct, unlocking all the supports will result in no change to the beam. Each support is now free to rotate in the LabVIEW interface with our applied moments on each support. All the supports are now physically unlocked, and as you will see momentarily, there is no change in the beam, proving our prediction correct. Once again, our shear, bending moment, slope, and deflection diagrams are identical to what we had in the initial step. Here you can see a side-by-side comparison of our initial fixed condition and our final simulated support condition. As you can see, the two sets of diagrams are virtually identical. Despite this being a relatively simple two-span beam, the moment distribution method is highly versatile and can be applied broadly using the same principles just presented. We hope you enjoyed this demonstration, and thank you for watching.